Okay, yeah, that looks perfect. Good, good, good.
So now you see.
Yeah, it's changing. We see your pointer.
Okay.
Very good.
Just a request. Please remind me 5 minutes before the deadline.
Okay, will do. Yeah.
Thank you.
Okay, good. Yeah, let's give it like 40 more seconds, because then we'll be fine. The goal is to start every talk on time so that people can tune in when they intended to see a particular speaker. And also not to, good form to maintain a good,
So how
good
much
schedule.
time I have? 35.
You have 25.
25. Okay.
Is your but I mean, we plus 5 minutes for discussion, so we assume that there will be questions in between. So
Okay. Thank you.
okay, so again, welcome everybody to this morning session. The next speaker is going to be RajeevSingh, and Rajeev, the floor is yours.
Thank you very much. First of all, thank you very much for a PhD student like me to give a platform like this to talk about our research, PhD research. So my title is Spin Hydrodynamics for Relativistic Heavy Ion Collisions, and these are my supervisors, and these are two primary references which you can go and look for more technical details. So I'll just give a brief overview of just answering just three questions: why, how, and what. For more mathematical and technical details, if we can ask, we can discuss later, or we can discuss during the talk. You can interrupt me anytime you want. So yes. So first, I'll start with why. Why I'm doing this research in the first place. So this is the plot which gives we show that the first positive measurements of global spin polarization of lambda hyperons. First of all, why? What is spin polarization? Spin polarization meaning the orientation of the spin of the hyperon particle relative to the angular momentum. And the second is why spin polarization of lambda hyperons? Because lambda hyperons have the very common decay, and the decay time is very long than the other hadrons, and it is difficult to measure the spin direction of the most hadrons emitted in the heavy ion collision. However, lambda hyperons are self-analyzing, meaning that in the weak decay, the proton tends to be emitted along the spin direction of the parent hyperon. So if we can measure the protons, then indirectly we can measure the hyperons. So this is the plot for the global spin polarization, which is this is average spin polarization with center of mass, and you can see that as it increases with the decrease of center of mass, and this is a plot by the Rick, and 200 GeV is the top Rick energy. So this plot and this result has been discussed and reproduced by many of the theoretical models, but still there is one problem. I'll tell you later. And it has been proved that this is a hottest, least viscous, and now the most vertical fluid ever produced in the lab in nature. At least means it has been not shown in it outside our solar system, or even outside our Earth, that that anything is have vorticity more than this. So before going to discuss what uh, we are doing, let me just have a little more explanation that non-central relativistic heavy ion collisions creates a global rotation of matter, which in analogy of Einstein-Gias effect and Barnett effect. What is Einstein-Gias and Barnett effect? Some message. Okay. Yeah. So what is Einstein-Gias effect? It's when a system of particles are placed under the external magnetic field, it tends to rotate, and on average, the particles are tend to align along the angular momentum. And just opposite effect has been shown again, given in that year, which is called Barnett effect, that when a system of particles begins to rotate, then because of this the conservation of total angular momentum, on average the particles tends to align along the system's angular momentum. So these two effects are the analogies of the non-relativistic uh, quantum mechanics, which means currently the people try to find the relative region between the relativistic heavy ion collisions and the non-relativistic quantum mechanics. So what I was saying that in heavy ion collision, all the emerging particles are expected to be globally polarized with their spins on average pointing to the along the system's angular momentum. So just like the previous speaker told that this looks like a pancakes because of the Lorentz contraction, and this is the schematic plot of the non-central heavy ion collisions. And these are called participants because these participate in the collisions, and these are called spectators, which does not participate in the collision. And because of these spectators, when we study spectators, we can find the value of average value of the angular momentum. So what other people are doing, other means the other groups like Bjorken group or the Frankfurt group study this spin polarization at the freeze out. Freeze out meaning there are two types of freeze out actually, thermal freeze out and kinetic freeze out. And freeze out meaning the particles will not interact from that point. That point is called freeze out point. So spin polarization is of particles are studied at the freeze out and where the basic hydrodynamic quantity is the thermal vorticity. So the point is that at the freeze out, they think that spin polarization is linked directly to the thermal vorticity. This is thermal vorticity, and this is become nu, which is the ratio of the fluid flow vector over local temperature. So the problem is that Rick also plotted or also gave the results of longitudinal spin polarization. Longitudinal spin polarization meaning spin polarization along the beam axis. So, but currently the theoretical groups have not explained or reproduced the results of the longitudinal spin polarization of Rick, and there is a mismatch of the sign. You can see here this is minus plus, but according to Rick, this is inverse plus minus. So that discrepancy is still there. So therefore, we are not able to explain this spin polarization effect of lambda hyperons completely. So I'll now say about our framework. So this framework is actually the framework which have the hydrodynamics, which includes the spin degrees of freedom. And this is the first this is the first kind of framework which has been which is there in the market. And this talk is about the first model which we have studied using this framework. So this is like a exploratory work, meaning that what will happen if I use this framework for a very simple system like a Bjorken model or Bjorken geometry. So in this framework, we will first study the perfect fluid hydrodynamic equations, which is without spin, and then we will determine the spin evolution on this hydrodynamic background. And then to compare our results to the experimental data, we have to determine the Pauli-Lomansky vector on the freeze-out hypersurface, and then we will calculate the spin polarization of particles in their rest frame, in the particle rest frame. And this spin polarization is a function of particle momenta, which can directly be compared with the experiment. In this talk, I'm not trying to compare with the experiment, but I'm just trying to give a formalism how we can compare with the experiment. Okay. So this work means we use the relativistic hydrodynamic equations to determine the space-time evolution of the spin polarization based on this GLW form of energy momentum and spin tensors, which is given in this book. And why we are using this form of energy momentum spin tensor is because from the hydrodynamical point of view, we need to have the symmetric energy momentum tensor so that the spin tensor will be conserved. I will show you later how, but we need to have the symmetric energy momentum tensor. And GLW form of energy momentum tensor are symmetric because they use some type of pseudo gauge. Uh, yes. And then we are doing this calculation for the Bjorken geometry and the transversely homogeneous setup. And we saw how this formalism can be used to determine the physical observables related to the spin polarization. One more important fact is that uh, we have restricted ourselves to the very small value of spin polarization, meaning we have restricted ourselves to the leading over terms in the omega mu nu. What is omega mu nu is the spin polarizing tensor, and this is actually the most important formula or the term in our framework, which is here. So according means any rank 2 antisymmetric matrix can be decomposed in this form. So here, what is kappa and omega? Kappa and omega will give us the 6 independent components, spin components, and which we study here, and then we will calculate the spin polarization of particles based on that spin components. And here kappa and omega are orthogonal to U, therefore we can write in this form. And epsilon is a total antisymmetric Levi-Civita tensor. Okay, please ask whatever you have during the talk. So now, just as I said that we need to find the hydrodynamical background. For that, we need to solve two conservation of charge and conservation of energy linear momentum. So conservation of charge is given in this form, where uh, for the ideal relativistic gas of massive particles, you can find in this the formula like this: n equal to 4 sin s xi n0t, and n0t is the number density for the spinless and neutral massive Boltzmann particles, which can be calculated in this form. And this accounts for the spin degeneracy and presence of both particles and antiparticles in the system. And this is the ratio of the mu over Q. Mu is barium chemical potential over temperature. So for the ideal relativistic gas of massive particles, this is the form. Similarly, for the conservation of energy linear momentum, we have used ideal relativistic gas of massive particles, and there we have this perfect fluid form. Okay, you remember I said that we are restricting ourselves here for leading order values of omega mu nu, this one. So if I use large spin omega mu nu, large spin polarization, then because of that large spin polarization, this laws, this one and this one will have contribution from the omega mu nu. Therefore, we are not doing that will be more complicated to solve analytically. So so uh, so now that because of that, we are just restricting ourselves to small spin polarization. And this perfect fluid form, this epsilon and p energy density and pressure can be calculated in this form, where epsilon 0 and p 0 same as before are for the spinless ideal gas and neutral massive particles. And this also can be calculated in this form, where K1 and K2 are the modified Bessel functions of the first and second kind. Okay, now these two conservation laws have 5 unknowns, uh, which is the flow, 3 independent components of the flow, and mu and T. Mu is the barium chemical potential. So since we already know what is the flow in our case, that is the Bjorken flow, so we just need to solve for mu and t, which will give us the perfect fluid hydrodynamical background. Okay. So why I was saying that we are using GLW form of energy momentum in spin tensor, because in the, like, we know that this is the form for the total angular momentum, which consists of orbital and spin, which can be written in this form. So since we know that total angular momentum conserve, so because of that we have this yeah this part. So we need to have this symmetric to make the spin conserve. Otherwise, it will not be conserved. For example, in the case of canonical energy momentum tensor, which comes from the Dirac-Lagrangian, T mu is not symmetric. T mu is anti-symmetric. So in that case, spin is not conserved. So that is why we are using GLW form of energy momentum tensor, so that we can make the spin conserve separately. Okay. Now this is the conservation of spin angular momentum, where S spin density is given in this form. Okay. One more thing, that all these three laws, spin, energy, linear momentum, and Barium number, can also be derived um, consistently from the quantum kinetic theory. So that is also one of the proof, or uh, one of the proof that this laws and this framework is on the right track. So this is the form of the spin tensor, where this auxiliary tensor is in this form. So this is looks complicated, but this is not, because is delta is actually the spatial projection operator, which is orthogonal to u, and a0 b0 are given from the background, which we need to solve first, and then we just need to solve this, which will give us the six evolution equations. How? I will tell you little later. Okay. Now to solve the spin equation, we need to have some basis vectors. So for our case, we just as we have using Bush invariance and transversely homogeneous setup, so we need to have this flow vector and this kind of other basis vectors, which is orthogonal to u and each other. And these are the normalizing conditions, where eta is the space-time rapidity and tau is the longitudinal proper time. Okay, this is the simplest model on which we can use our framework to see how this works actually. And this works quite fine, at least till now. And the matrix signature is plus minus minus. So you can see from the conditions that U is a time-like basis vector, and X, Y, Z are the space-like basis vector. Okay. This is it's not much required to say, but I'll just say that I have used this UXYZ in the omega mu nu, which is here, and just we got this main, we got this the general form of omega mu nu spin polarizing tensor, and you can see that, which I was saying earlier, that kappa and omega will give us six independent components, which is here C kappa x, kappa y, kappa z, omega x, omega y, omega z. So these six independent components will give us the spin polarization evolution, which will tell us about the spin polarization of particles when we calculate the Pauli-Levinsky vector. Okay, so for the Bjorken flow and the transversely homogeneous setup, we have these two conservation laws to be solved, which is here, and this is pretty much easy to calculate analytically. So we have this, we can be the clock is shown later, and for the spin tensor, we will just use this six combination of the uh, basis vectors, and this method is called projection method. What we do is that we take six combination of basic vectors, and we project them in onto this conservation law. So that will give us the six evolution equations for six components. But in this case, we can see that six components are actually decoupled from each other, because we see here that this is very simple model, and so the six independent components are decoupled from each other. But if I go for 2+1 or 3+1 systems, which we are doing now, then these are not decoupled from each other. So in this case, this can be solved analytically, and we have plotted this in the components with respect to proper time. So these are this is the plot for the barium chemical potential and temperature. This is the plot for the barium chemical potential with temperature, and this is the temperature. So you can see that we have reproduced the well established that temperature should decrease with proper time, and this ratio should increase with proper time. And these are the initial conditions. Now one can say that REAC and LSC have barium chemical potential very low, uh, but we have very high. So the thing is that we are not actually here in this talk, in this paper, we are not comparing with the data. We are just seeing what will happen if I use our framework for a very simple model. So this is just like a exploratory work for our new framework, and this is the evolution time. And this is the plot for the spin components, where you can see that C kappa Z is actually having a strong time dependence than the other spin components. You may wonder why C kappa Y and C omega Y is not there, because C kappa Y and C omega Y are having the same form of differential equation as C kappa X and C omega X. Therefore, it is better here not to plug C kappa Y and C kappa Z, because it will have the same form of C kappa X and C omega X. Okay, so this is the formula for the Pauli-Levinsky vector, and this is the ratio of and this ratio is the formula for average spin polarization, and this is required to be solved so that we can we can get the results for the spin polarization at the free zone. Uh, these two integrals have to be solved. This is integral for momentum density, and this is for Pauli-Levinsky vector, which has to be solved to get this average spin polarization per particle. Okay, and this is the freeze out hypersurface, which in this case is like this form, which is in terms of u lambda, means fluid flow vector and proper time and rapidity, and p is the particle form momentum. Yeah, yes. So to compare with the experimental data, we need to have we have to boost the average spin polarization to the local reaction of the particle using canonical boost. And after boosting, we got this whole uh, matrix. You can see that uh, this is in the form of particle momentum px and py, and this has been and yes, px and py, and yp is the rapidity in this case, and chi is the ratio of the k0 plus k2 by k1. K0 is the modified Bessel function of the zero kind. So if I plot this three components, pi star 1, pi star 2, pi star z, then this will give us the plot for the plot for the average spin polarization, and pi star 3 or pi star z will give us the longitudinal spin polarization of the particle, which is the main goal for us to match with the experimental data. So one usually argues that the total angular momentum during the original collision process has only orbital part, which is perpendicular to the reaction plane, and direction of the angular momentum 3 vector is opposite to the direction of y-axis. So it is expected that due to total angular momentum conservation, after the collision, certain fraction of initial orbital angular momentum is transferred to the spin degrees of freedom. So in order to address this physical physics or to address this physics, we assume that the initial spin angular momentum has the same direction as the total angular momentum. So in this numerical analysis, we have taken or we have assumed that all the C coefficients except C omega y is 0, the initial values, and the initial value for C omega y is 0.1, and these are the initial values for the barium chemical potential and temperature. So we numerically solve this pi spin components equation for spin components and plot the average spin polarization per particle after boosting, and as expected we see that pi star y components is negative, which reflects the choice of direction of the initial spin angular momentum of the system, and longitudinal rapidity is vanishing completely in the mid rapidity, which is not the case in the experimental data, and we did not have any goal from this talk that we have to match to the experimental data or not. So but here we see that we have got quadruple structure in the pi star x component. Okay, finally, in this work, we have presented the first chemical results describing the space-time evolution of spin polarization tensor in the hydrodynamical post-King variant background. Our formalism was based on the forms of the energy momentum tensor and the spin tensor given by GLW or the Groot, Van Leeuwen, von Weert, and we consider linear terms in the spin polarizing tensor. This procedure allows us to solve first the standard perfect fluid equations and subsequently to consider spin polarization in a well-defined hydrodynamical background. Our results demonstrate that 6 scalar functions, which are 6 c kappa x, c kappa y, c kappa g, and c omega x, c omega y, and c omega g, in this case, in the Bush invariant case, evolve independently. So, and their proper time dependence is rather weak, which allows us for consistent treatment of linear terms. So, the results of the hydrodynamic calculations can be further used to determine the spin polarization of particles on the freeze-out hypersurface. But our results cannot reproduce an experimental the quadruple structure of the longitudinal polarization because of the symmetries which we have assumed. So, so this is the plot for the longitudinal polarization, which which Rick have shown, but now currently no hierarchical group has yet has able to reproduce this feature of the spin polarization. So this is our main goal, and we are using this our framework for the 3+1 numerical simulation, and we hope that our framework will be able to solve this problem, this discrepancy. Thank you.
Yeah, thank you very much, Rajeev, for your nice talk. Do we have questions? Anybody? Oh yeah, Janis.
Yeah, thank you, Rajeev, for the nice talk. I wanted to ask you if you could explain again why you used a symmetric energy momentum tensor.
Okay. Yeah, we know this form J equal to L plus S, and we know that this means this values. So if I means differentiate this equation, we will get this form del mu S equal to T nu mu minus T mu nu. So to make the spin conserve, we have to have this symmetric energy momentum tensor. Otherwise, gas will not be conserved. Like for example, in the Dirac energy momentum tensor.
Yeah, I understand that, but why do you want to focus on a conserved spin tensor? Why not allow for the exchange of angular momentum with a spin?
Okay. Yes, this is one of the approach by other groups, but we see or we consider that the spin polarization is a macroscopic observable. What we see in the what we see in the rig is that spin polarization is not that small that it will come in the quantum corrections. So the spin and angular momentum conversion happens in the first order or the higher order terms, but we consider here that the spin polarization comes from the leading order, and for that means that is a macroscopic observable, and for this we need to have the spin degrees of freedom which have to be conserved.
Okay, I understand. Thanks.
Thanks for the question. Ayan, you have a question.
Yeah, thank you, Rajeev, for the talk. I wanted to ask if you have some sort of a thermodynamic description for this spin current, spin tensor, in the sense of like if you have you have a vorticity or as some analog of a chemical potential. Would you be able to describe this in a thermodynamic way?
Okay, first of all, means we see we assume that the spin polarization tensor is independent of thermal vorticity, and yes, we can describe this in the from the thermal approach, which is means we have the paper longitudinal polarization from the thermal model, which you can have a look. But yes, we can do it. But the important assumption is that we see the spin polarization tensor is independent of thermal vorticity here in this framework. They may link in the higher order terms, but in the leading order, both are independent. This is our main assumption.
Yeah, but you would like the whole system to relax to some kind of thermal equilibrium, right? And in thermal equilibrium, this should vanish unless there is a chemical potential for it, like some rotation or something of the system that you're doing. So 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 how is this? I mean, if you want to put in some, for example, an entropy current or something, it should lead to dissipation of this spin tensor, right? So there should be some sort of a thermal description, right?
Yes.
To understand.
Yes. From the thermal approach, so we have not done the entropy current analysis till now, but we are still on the very first phase, so we will have this in mind.
Thanks.
So maybe following up on Ayan's question, so I agree that there should be something changing the thermodynamics if you include new degrees of freedom, if you include spin in your statistical mechanics with description of the system. The way that you seem to set it up, and I'm just naively looking at it, I don't claim that I understand all the details. The way it seems you're setting it up, because the spin is conserved in its own right, the spin current, it almost seems to me like you could think of the spin itself as a charge, like you would have normally an electric charge.
Yes.
And it undergoes the same same types of dissipation and transport as any, like an electric charge.
Yes.
And then if that is the case, then yes, then you would add the spin momentum just as a separate equation to your conservation equations, and you would write down the spin current as just like you would an electric current constitutive relation. And so in that sense, I would think that you could, in the thermodynamic sense, also add the spin charge as a coupled to some source, like you would put in an electric charge coupled to the chemical potential. So that's how I would imagine it should go. It should appear there should be some kind of spin chemical potential that you can define and then identify.
Yes.
Which, I mean, I don't want to hog the discussion, but maybe this might be an interesting aspect for the holography community, one like where people have developed a more geometric view of hydrodynamics. So you think of the energy momentum tensor as being sourced in a curved space-time by a metric, and then you calculate it, and then in the end you evaluate it at the flat metric. Right, so it's a more geometric point of view, and then I think it would be interesting to take a look at this this system way of spin degrees of freedom in more of such a geometric view, where then when you have the full glory of spin connections that couple now or that play along with the metric, and then one probably has to use first order formalism of gravity. And so then you can I mean, because that's the standard idea, right? You put your hydro fluid into some sort of curved space-time, calculate your things, whatever you want to set up, and then in the end, in order to get 1-point functions, you vary with respect to that metric, that fake curved metric, and then you set it in the end to the flat metric to get the energy momentum tensor that you wanted. And I believe this would be an interesting way of looking at the system as well.
Thank you. I think it would be better if you can refer some papers to have a look to this type of approaches.
In fact, I know one. So there has been a study by Gallegos and Gorsoi who take this approach in the section 2 or 3 of their paper. This should be the reference. I'm posting it in the chat so that everyone can see it.
Thank you.
So Gallegos and Gorsoi earlier this year, in April this year, they have that point of view in that paper, and they also have a fluid gravity calculation in a fluid in a gravitational model like Lovelock gravity. So just to connect maybe to something that holography could contribute here.
Thank you very much.
Any other questions?
Matthias, yes, I have a question.
Okay.
Rajeev, thank you for the talk. I would like to say that to me it is still mysterious why you do not couple the spin to the vorticity in your framework. Is there any specific reason for that? Because from the chiral vortical effect, we understand that it is possible these two couple to each other.
Yes, of course it's possible, and this is one of the approach by many people doing this kind of calculations. But here we assume that this is independent, and this comes out naturally from the heavy ion collisions. We see that spin polarization should be like what Matthias said, that it's independent, and it's what's the word? I forgot the word. But we do not assume that it is dependent on the thermal vorticity or something.
Yeah. Okay, thanks.
So that's a bit of a more phenomenological reason and approach that you use as an assumption in your description.
So theoretically, it is possible to consider that. No.
What? Which one? Theoretically, nothing is proven till now. At least that I can say that whether thermal vorticity is linked with spin polarization tensor or not, both are just assumptions. So we cannot say that this is true or that is true. Only we can this can be proven when we have the 3+1 numerical simulation which can reproduce the data.
So, okay, good. But my question is it possible to add a term containing the coupling between vorticity and
yes.
spin? Okay, good. That's my question. And then we can fix the coefficient with the experiment and whatever we want. Okay,
and
good,
GAC linking what you're saying GAC will come in the higher orders. So GAC we are going now.
Why? I think vorticity is of first order, and you're studying dissipation in your study. So why don't?
In the first Kagar only. GAC is means in the zero Kagar we see GAC independent. This is independent spin polarization and thermal vorticity. And in the first Kagar we say that these are combined or these are linked, or this comes from thermal vorticity.
Okay, thank you.
Okay, any other questions? That seems not to be the case. We still have time, a few minutes. So if you have any ideas, any thoughts.
Yeah, any comments, any criticism would be good. Or any other approach.
I already gave you what came to mind.
Yeah, thank you. Yeah, I
Comment
think
on-
Omar Gosar also talked about his work in the spin hydro workshop, which was last week, I suppose. Last week.
Maybe I can refer. Maybe we can refer people to also that conference before Yannis asks his makes his next comment. There was last week. There was a conference organized by the ECT Star Institute in Italy, and so what was the exact title again?
No, just a second. Just give it to you.
Yeah, spin hydrodynamics, something like that. Yeah, okay. And there were a couple of interesting talks. So if you're interested, then just write me and I'll give you a link. Just but otherwise you can just Google ECT Star and spin hydrodynamics and you will find the conference.
Yeah, I gave the link. You can find most of the people of the spin hydro community have talked about the work.
Okay, great. Yeah, so if you're interested in that, you can look at the link that Rajeev just posted. But yeah, Yannis, you had a comment.
Yeah, so for the geometric picture you gave earlier for the spin tensor. So from gravity, we know that the source, the geometric source of spin is the spin connection, as you said. But the derivative of the spin connection is the curvature, which is second order in derivatives. So that for me means that the spin connection should be first order. So I don't see how you can get an equilibrium partition function directly from this geometric reasoning if you don't go to first order in derivatives. So that's a comment. And the second comment is that for the vorticity thing, I think that if you can define the spin chemical potential as the gradient of the vorticity or something like that, you can absorb the vorticity into the definition of your thermal velocity profile, so you can basically set it to 0. That's why you don't really need to include it here in the equilibrium, I think. I'm not sure. So it's basically like the Unruh effect rotation, if you want.
Yeah, thanks for the comments. There might be some points like that discussed in the Geiger-Sgursoi paper. I don't remember I don't remember these 2 points, but thanks for the comments. So then, any other points? It looks like we are also nearing the time for the next talk. So if there are no other questions, then Rajeev, thank you very much again.
Thank you very much, sir.
And the last person in this session is going to be Emil, right? Emil Have. Hi.
Yes, indeed.
Okay, very good. So could you bring on your slides so we can check if it's working out?
Yeah. Let me see.
Yeah, it looks good, except there's the box, which is probably a Zoom.
Yeah, this is the Zoom box, so it should be gone now, and this should be gone too.
Yep, this looks good. I see the slides. I see